Okay, so this is the second day of the class on soil dynamics 7141. Last week we had the first class and we introduced everybody, and I also introduced myself and Alex. Alex is he's the teaching assistant for this course. He's currently a PhD student at National Taipei University of Technology. And Alex will jump in and help me out if if I have a long assignment from work and if I'm not able to attend or conduct the class remotely. That's when you'll see Alex, but we'll give advance notice on that. And also there is Fakadu Ubetu. He's a course coordinator at BiT. So you will hear from him more often, distributing materials, homework assignments, projects. That's where you deliver. And he would be the main guy for, grading homeworks, projects, and also midterm and final exam. So your communication would be with Fakadu most of the time. But you can send any questions to me and Alex through email. So just to briefly touch the course content, we have 9 chapters. The first 4 chapters, Introduction to Earthquake, Theory of Vibration, Wave Propagation in Elastic Media, and Strong Ground Motion. These are more understanding the concepts of the earthquake course. But the last 5, starting from dynamic soil properties and dynamic earth pressure problems and retaining walls, and air-raised tank design of geotechnical structures, and liquefaction of soils, and introduction to ground response analysis, soil structure interaction analysis. This last 5 chapter is where you see the application of the course. So the first 4, it's basically understand the concept of earthquake, the concept of vibration and wave propagation, how we record it, how we bring it to use. The last 5 is where we apply it for geotechnical engineering. So in terms of references, we talk the first 2, Geotechnical Earthquake Engineering by Stephen L. Kramer and Principle of Soil Dynamics by Praja M. Das. These are the main references we'll be using. But the other 4 by Prakash, Soil Dynamics by Prakash, and Vibration of Soil Foundations, Fundamental of Soil Dynamics by Prasad, and the Anil K. Chopra book also. We'll have some sections touching all these references, and the other main references in online resources, articles and pictures. You'll find most of the slides full of pictures, full of images. That's just to make the class understanding easier. So even if the slides look like, they are 50, 60, 70 pages, mostly they are full of images from online resources. In terms of grading, we talked it's 50% is homework and mini projects, so you have to be very serious on deadlines and submitting those. And the mid and final exam covers the other 50%. So that was just a revision of what we discussed last week. And last week also, we started chapter 1, which is Introduction to Earthquake. And there we define terminologies, and we saw earthquake causes, theories, and world high seismic areas, and example of previous damage by previous earthquake, and taking especially the 2004 Indonesia, Sumatra earthquake, the 2011 Japan earthquake, the 1985 Mexico City earthquake, and the 1964 Japan Niigata earthquake. So we have seen these examples, and we discussed the last part was at seismic waves. So we'll quickly go through it. So this is terminologies we have discussed already, and we have seen the causes of earthquakes and previously recorded data of earthquake, which is along the boundary of those fault lines. And we have seen how many types of faults we have: the normal fault, So we have types of faults: the normal fault, the reverse fault, and the strike slip fault. And we discussed briefly on the interior of the Earth and its content. Fakado already joined. Okay, we started the class, Fakado. Welcome to the class. And we have seen the theory of the continental drift and why the continents are drifting away from each other and the reason behind it, and some evidences such as the shape matching, similar fossils finding around different continents, and similar climate and similar rock discoveries. So based on that, the continental drift theory says, okay, the continents must be drifting away from each other. So this is what we used to be 250 million years ago and through time until the present time. And continental drift theory tried to support that drifting theory using the reason behind it as the convection currents, the molten rocks within inside of Earth, those causing the top plates to move around. And other theories, plate tectonic, which is also embracing the continental drift theory and stating that this continent, especially the 7 major pieces or plates, they must be going away from each other. In some cases, you see something like this, converging to each other, or you may see like a strike slip like this, which is a western part of US. It's a strike slip. So in the converging case, strike slip case, we usually see more larger magnitude of earthquakes occurring. But in the diverging case, you have like African plate. If you consider it around here, it's a diverging plate. So those are, we don't expect larger earthquakes in that case. And the other theory is elastic rebound theory, which go more on the strain development, energy development on the rocks and how it breaks and generates earthquake energy and the related vibration. And we have seen these convergent plate movements around tectonic plate boundaries, oceanic convergence. You may have ocean and you may have this lithosphere under the ocean. So one subducting under the other one, this converging through time. We're talking in geological time, sometimes decades, 100 years to 100 years. So the energy accumulates at some point, the rock breaks, then you have earthquakes generated. So those convergences can be under ocean convergence, or oceanic continental convergence, where there is a continent, the earth, and then the ocean. Or you can have continental convergence. And a good example would be the Himalaya, the formation of the Himalayan mountain. So the mountain is growing every year. It's expected from 3 to 6 centimeters a year. And this is because the Indian plate is moving north and around, I think, 9 centimeters per year. The Eurasian plate is resisting that motion. The Eurasian plate is Russia and Europe. And because of that convergence, you see some part of the plate, the Indian plate, goes under, some part of it goes up, creating, the height of the mountain. We have seen the high seismic areas, which we normally call the ring of fire. If you Google the ring of fire, these are the images you would see, which means the high seismic areas. This is where the converging plates and the strike slip fault boundaries are found. So this is usually the western side of South America, the western side of North America, and the eastern part of Asia, around Japan, and the eastern part of Australia. All this around the Pacific Ocean, that's the ring of fire. This is where most of the larger earthquakes occur. I think the largest earthquake, which is 9.5, it occurred in Chile, the west side of Chile, which is around here, South America. This is another high seismic area showing just with contours. And we also briefly discussed the fault activity in the African Rift Valley, because this course is specifically for Ethiopian University in Bahar Dar, BIT. So we briefly discussed what's happening in the African plate, even if it doesn't generate high seismic areas, but we still have intraplate fault activity within the eastern part of Africa. So we know that it's a diverging fault activity in the Rift Valley, the Somalian plate going to the southeast, and the rest of the main African plate going to the northwest. And the reason behind is some volcanic activity or those convection currents. So some cracks already observed, in the Rift Valley, major cracks forming, but in the final stage, millions of years from now, what is expected is there are different models showing the eastern part of Africa separating itself. Can be these two pieces, or there are models showing only just one piece. This is just the expectation millions of years from now. And there is another research from University of Bristol, which also says, hey, before the separation of the East African plate, there may be flooding before that, because there is only a piece of rock about, I think, 20-meter rock, which is blocking the Red Sea. So if we dig this, we may have a chance, like, some lakes forming. That's a research. You can Google and find it. There are so many researches going on in the African Rift Valley nowadays. And we have seen some examples of previous earthquakes, some tsunami damage, especially the Indonesian earthquake causing tsunami and devastating earthquakes. Tsunami it's the worst. The earthquake itself, the shaking, it doesn't have that much energy to cause this much destruction. But the tsunami, the high water coming, which can be 20, 30 meter high, it's like flooding the entire area and destroying it. And the other damage was by the 2011 Japan earthquake, which is a subduction area, and it caused also tsunami and flooding. The entire beach area is flooded in nearby cities. But it also caused, there were nuclear power plants nearby, and those nuclear power plants, they were not designed for that level of high tsunami. So the protection was not good enough to stop it. And the entire area of the nuclear site was flooded, so cooling could not be happen on time. And there was pressure building and partial or complete meltdown occurring and then exploding. So that nuclear accident, it's the worst in the sense that people can no more come back to their city or their village, at least within 20-kilometer radius. So it's like a permanent loss. But the good thing is, on the other side, the nuclear itself didn't kill people because you have time to escape the area. The explosion happened, I think, within 3 to 5 days after the earthquake. And a tsunami occurred within 7 to 10 hours. So there was a tsunami warning. Most people left and the area. Then there was a nuclear pressure building for explosion, for radiation, but there was enough warning. There was enough time, 3 to 5 days. So people already left the area. So the nuclear by itself, it didn't kill people, but it caused a permanent damage to the area. Maybe in the next decades and 100 years, the cleanup will take a long time. So it's like a permanent loss in the sense that they cannot come back to their home, in a few years. The other one is the Niigata, Japan earthquake. This is a phenomenon called the liquefaction, where, if you have a loose sand deposit, the ground underneath of the buildings is very unstable. It becomes more liquid, and buildings, settle, get destroyed, or the water comes out, cause a larger, settlement within the ground. So it creates a huge instability. And so you'll see, we have in the Niigata, buildings have been, falling. a partial displacement, partial settlement, or some areas get watery and liquid, so some cars and objects being swallowed. The other example we have seen in the Mexico City earthquake. This one is another phenomena called resonance. Resonance is like when you have a magnified amplification, because the period of the motion of the soil coincides with the period of the structures. Then you have much amplified motion. So that's, if you have a rock motion like this, the soil amplifies a lot. This is the magnitude you have. And it coincides with certain buildings period. We'll see what period is. Every object, it has its own period, or it has its own fundamental frequency where it vibrates. When things vibrate, when we say period, it's the time it takes for one complete cycle. If you have a building like this, if it vibrates back and forth, let's say goes this way, vibration, then comes back and passes the neutral location, and then comes back to its original position. This vibration, if you take its one cycle, the time it takes through, to make one cycle, we call it period. So depending on the stiffness, taller buildings, they take longer time. Shorter buildings, they take shorter time. So that period, when the period of the soil has its own period. The structures, depending on the framing, everything, they have their own period. So if the periods are close to each other, there is a phenomena called amplify resonance. And that resonance means the motion will be amplified a lot. So because of this Mexico City earthquake, the ground is like a loose clay deposit. It amplified the motion. Then those buildings which have, especially from 5 to 15 story height, they have a period of around 2 seconds. And the soil is 2 seconds. We'll see the detail of what this calculation look like, I believe, in chapter 3 or in chapter 2 and 3. But when you have periods close to each other, then that's when resonance happens. And shorter buildings from 5 to 10 up to 15 story buildings, they get damaged a lot. But taller ones, which have a period of larger, let's say 5 seconds like that, they survived. That's what these amplifications, that's what this model is also telling. Like taller buildings or stiffer buildings, shorter buildings, they didn't get damaged. But certain buildings with a period around 2 seconds, they suffered a lot. That 2 seconds is this. If you see it in the earthquake response spectra, at around 2 seconds is where the maximum amplification occurred. So if you have a period of 2 seconds, that's when the most damage occurs. So this is just a perfect example. A shorter building, story building, is getting collapsed, destroyed, but a taller one survived it. Just a minor damage, like windows or minor cracks like that. Another just plan view showing how there are 2 earthquakes in Mexico, 2017 and 1985. The 1985, the blue one, which damaged lots of buildings. But after that, there was an effort, the code revised, and the building code get more restriction on designers. So in 1985, another earthquake occurs, but less damage. Other earthquake damage on civil structures, you can have landslides. Just the portion of the mountain, landslide can occur because of rain, leaking water through the failure surface, or if there is an earthquake around it, that can speed up the occurrence of the landslide. And other bridges falling, buildings inclining. So this was a quick revision of what we discussed last week. So we can start today's class in detail from the seismic waves. We touched it a little bit last week. The waves is, we need to understand what waves are so that we know how earthquake travel from the focal point where it occurred and to going to other areas. If you see the picture on the right side, let's say an earthquake occurred right here. There are body waves which travel inside the Earth. So we call them body waves. There are these body waves, they also travel right directly above it. But once these body waves hit the surface, they convert into also a surface wave. So on the surface of the ground, we will see waves. We call them surface waves. So seismic wave, we can divide it into two. Body waves, which go inside of the Earth, and surface waves, which are going on the surface. The surface waves, we have lava waves and relay waves. We'll see the detail shortly. And the body waves, we have primary waves and secondary waves. Primary waves, we call it P wave. These are the first wave to arrive in a recording station. After a few seconds, you will have a secondary wave. The secondary wave, also called the shear wave, we'll see. Secondary wave can be divided into further SH, a shear wave, horizontally propagating, and a S wave, SV, vertically propagating. So if you see this, these are just models trying to describe what those waves look like. If you see it on the left side, the P wave and S wave, these are the body waves. So the P wave, which is a primary wave, the first wave to arrive to a recording station, it moves in a fashion that, you know, the interior of the solid, it expands at some points like this, or it compresses at other areas. So it's like if you hit an object directly in the axial direction like this, the way that wave propagates, this is the direction of propagation, the red arrow. There is compression in one place, then relaxation in the other, or expansion. That's how the wave travels. So the particle movement is in the same direction to the wave propagation. When we say particle, you know, the local point is movement. The local points, they don't move. And in case of S wave, in S wave, let's say if you give it an input motion like this, sideways, like a shear wave. S waves are also called shear waves. So what it's doing is the particles are moving in the perpendicular direction compared to the wave propagation direction. So it's like up and down motion. But the wave is traveling in this direction generally. But the local particles, you see them moving up and down. It's like the energy propagating. In the lava waves, these are surface waves. We see them on the surface. The body waves, we don't see them. This is how they travel inside, deep inside the Earth. But the lava wave, once the body waves arrive to the surface, this is how the lava waves travel. So this is the ground surface. This is visible. You see the ground, the wave is propagating, let's say, in this direction to the right, but the particle can be sideways. That's what lava wave is. But our relay wave is like up and down. The particle moves like a rolling wave. It feels like if you are standing on this ground when the earthquake occurs, you feel like you are pushed up and down. If you are standing during an earthquake, you feel like you are being thrown sideways. So the P wave, just an example, if you have a spring attached to a wall or some fixed point, if you push it axially, you can see that the energy you are applying is propagating and finally reaching the wall. The way it reaches to the wall, because of it, there will be some expansion, there will be some compression on the spring, and that's how the wave it travels. Your disturbance, your input travels like that. That's just a perfect example for a P wave, how it travels through a solid object. So P waves, P, like I said, it stands for primary, and it can travel up to 8 to 13 kilometers per second. This is the fastest seismic wave. It arrived first in a recording station. And it is also called compressional wave. Its name comes from the fact that it compresses part of the compression and expansion created in the solid object when it travels. So that's where the word compressional wave comes. As a P wave passes, material compresses in the same direction, the wave is moving and then extends back to its original thickness. That's what the expansion and compression happen. So you can call it P wave, you can call it compression expansion wave. It's the same thing. P wave travel through liquids and gases as well as solids. So any material it can travel through solids, liquids, and gases. Although liquids and gas have zero rigidity, there is no shear stiffness for gases and liquids. But that doesn't matter for P wave. As far as it has elastic modulus, then it can travel through it, which is about axial stiffness. So, which means the compressibility. For example, in the air, it's not a seismic wave, but a sound wave or P wave moving through the air. The way sound moves through the air, it's by compression and expansion, like a P wave in a solid object. S wave or shear wave, they are called, S stand for secondary, because they arrive to the site, the recording site, after the primary wave. And its speed is about half the speed of P wave. S waves are shear waves. We call them shear waves because see how the motion is applied. It's in the shear direction. They move by material flexing or deforming sideways or shearing from the direction of wave travel. So this is the direction of wave travel you have, but the material, the local material moving in the perpendicular direction to compare to the main propagation of the wave. S wave can travel only through solids because only solids have rigidity. Since it is a shear wave, it needs to have a shear resistance for shear wave to pass through it. In the liquid, like in the oceans, there is no shear wave because water doesn't have a shear stiffness or it's near zero. So the shear wave don't propagate through liquids and gases. So with the spring model example, it's like applying a force up and down on the spring, then you see the spring moving up and down. So the local particles are moving up and down like this, but the main direction of propagation of the wave is perpendicular to that. So we call this shear waves. So this is, we'll come to this. It's a main concept, the fact that they are not traveling through liquids or water and gases. We'll see later in example why, because we'll derive the equations of these waves in chapter 3 in wave propagation. We'll go detail. There are partial derivative equations we'll derive and see what the equation, what the speed of this S wave, P wave looks like in different materials. Rayleigh wave, this is a surface wave. Now we are on the ground surface. A person can really stand on this and feel how the wave is traveling, underneath. In the surface wave, if your motion is like this, up and down, it feels like the local particles are moving like in a circle direction, like a rolling, and the ground it feels like undulating like this. So in that case, that's a Rayleigh wave. It's first discovered by a person called Lord Rayleigh. I think it's an English aristocrat. So if you have like a telecommunication cables, a power cables on the ground, this is what a Rayleigh wave can cause. Wherever it's going up and down, you can see ground cracks. Or the cables being, broken apart. The other surface waves are lava waves. Lava waves, what happens in case of lava wave is the ground just moving sideways. If you are standing on this, what you see is the ground just moving sideways. You are being shaken sideways. You don't feel that much like a rotating up and down motion. So if the ground is moving sideways, there is a wave traveling, which is perpendicular to the direction of the main wave propagation. That's what lava wave is. So all these terminologies, lava wave, Rayleigh wave, P wave, and shear wave. It's based on the direction of propagations, based on how the particles move compared to the main propagation direction of the wave. And in terms of recording earthquakes, earthquake travel, it generates as a focus point, then it travel, it come to the ground surface. If you have a ground like this, then we should have some recording stations recording the earthquake. So throughout the world, there are so many thousands of recording stations. So in the old days, when we record earthquake, we used to use something called seismograph, where it's deeply embedded into the ground like a bedrock. We'll put a recording instrument deep in the ground and attach it to the bedrock because we want the bedrock motion. Because the local soil around the surface, it can be affected by local. We have also recording station in the soil, but mainly we want the bedrock. And from the bedrock, we can have also a recording station, on the ground near to the soil. But once you have a soil property, you can easily do, site amplification to see how it propagates through the soil. So what you used to do is you have like instrument that seismograph attached to the bedrock. It can be bolted through here. We want to rigidly attach it so that it can feel the motion of the bedrock. And if you see this, there is a frame right here. This frame has a heavy weight, a heavy mass suspended with a wire or a spring. You'll see the design of this in theory of vibration. But it's designed in such a way that when the ground moves, all this, rigidly attached instrument also moves together. But this heavy mass doesn't move. It feels like it's at rest. And notice there is a pen attached at the bottom of the heavy weight. So what it does is, when this seismogram rolls, when this moves, and this is constantly rolling, so this pen makes a scratch on it. So seismogram is the whole instrument, and seismograph is the record. So you have these two terms. This is how we used to do, we record it. So we have a heavy mass. This is a big concept. We have a heavy mass suspended with wire. And when the entire thing is moving, this mass is not moving. The motion is relatively zero. I'll show you later how that is designed and work like that. Because this is a rolling, this is like a paper. So the pen scratches on it. So we get a record of it. So this record can be done, either we can get displacement, velocity, or acceleration, depending on how we calibrate this heavy mass. So finally, you have the seismogram, the record. If you see the record, when the earthquake occurs, you have the first wave arriving, which we call the P wave. Before the P wave, it's negligibly zero, or you may have some noise from vehicles or some wind action or anything disturbing. You may have very negligible motion, but you'll have significant motion as the P wave arrive. That's when we know earthquake occur. After the P wave arrive, after a few seconds, then we have the shear waves arriving to that recording station. So you have some gap here. It can be 10 seconds or 15 seconds, whatever. But the ground shaking is larger because the S wave shake it lateral. And after the S wave, now we will have the surface waves arriving, the lava wave and the relay waves. So if you see it on the picture at the bottom, initially you have a background noise, then a P wave arriving, then S wave, shear wave arriving. So we call this the duration between a P wave arrival time and S wave arrival time. We call it PS time interval. We'll use this term later to find the location of earthquake. So the first wave to arrive is the body waves. And then the surface waves arrives later, the lava wave and relay waves. So this is what the record look like. Nowadays, this is analog record. Nowadays, this is replaced by electronic record system or digital record system. So once an earthquake occurs, we don't really wait for to say recording station send this. These are converted. We are digitally. There are so many accelerometers nowadays, recording and instantly passing it online. So you can see the motion of an earthquake within minutes after the occurrence. So if we record an earthquake, now let's try to see, where it happened. How do we know where exactly it happened? How do we locate it? No, there are different methods. There is a three-circle method, which tells you the distance where it occurred from a recording station. Let's say you have, this is the Earth, an earthquake occurred right here. You have a recording station here. You have a recording station here. So the wave arrived right here. Now, when the two recording stations, or we may have another recording station here. Now, when the two occur, the distance, you can see the distance. Let's say this is the epicentral distance. This is directly above the ground, let's say. So you can determine this distance, d, with this equation. This equation is also given reference 1, Stephen L. Kramer, page 44. So the way they determine this equation, if you see the component of it, this is the duration, the time difference between the P wave and S wave. Remember in the seismogram before, we talked on this duration, the PS time interval. We know what time the P wave arrive. We know what time the S wave arrive. We know the time difference. That's the time difference right here. And the VS and VP you see here, they are soil properties. It's the shear wave velocity of the nearby soil, nearby ground, and the P wave property of the nearby ground. This has nothing to do with the seismic, but it's a local soil property, like density. It's a property of the soil. But we'll see how we determine for different ground conditions, how we determine shear wave and the P wave velocity. Now you can see the derivation of this equation from here. You don't find it in that reference book, but I found it somewhere, I think maybe online. It's an easy derivation. If you have the time for the S wave to travel distance, d is, distance by velocity. And for a P wave, it's the distance by the VP. Then if you subtract TS minus TP, finally you end up with this equation. And if you solve it for d, which is the distance, then you have this equation, which is similar to this equation. So, which means if an earthquake occurs at some point in the Earth, you can really determine the distance to the epicenter from a recording station D. This, you know it on the ground surface where it is. But now, let's say there is an earthquake occurred. We have these three recording stations, which is the three-circle method. The three-circle method is trying to use this concept, this distance concept, or this distance equation. Let's say an earthquake occurred. We have a recording station at somewhere, this yellow triangle, and we know it's the distance is D2. So make a circle. That D2 can be from that recording station. It can be anywhere, right? The earthquake can be here, can be here, can be here, anywhere. So, but we know that it's at a distance D2 from that recording station. So make a circle. We have another recording station somewhere else in the world, and it tells us the distance is D1 from that recording station. Make another circle. And from a recording station 3, we have a distance of D3. Make a circle. So what the three-circle method is saying that each recording station tells us the distance from them is this much. But if we have 3 recording stations at least, the common point where these circles meet should be the location where the earthquake is occurring, because it has to be true for all of them. It's a distance D3 from the location 3 recording station, distance D2 from location 2, distance D1 from location 1. So the common point is the one satisfying. It's true for all of them. So you need at least 3 recording stations to determine exactly where an earthquake occurred. That's what the 3-circle method is doing. Just to show you in 3D view, let's say an earthquake occurred somewhere in the Atlantic Ocean. And a recording station in Montreal, Canada, it states that, oh, the earthquake is about 8,400 kilometers from the epicentral distance. So you make that circle on the globe. But a recording station in Sao Paulo in Brazil, it states, well, the earthquake occurred 5,500 kilometers from them. So you make another circle. But you need a third location also. And there is a location, a recording station in Paris, in France. And that one showed the location of that earthquake is 6,700 kilometers from them. If you make these 3 circles, then the epicentral distance or the epicenter is found to be in Atlantic Ocean. That's how it's usually determined. This determination is now, it's automatic because the records are obtained digitally and they are processed digitally and automatically it tells you exactly where it is. Now, there may be some errors. It cannot be like 100% perfect with 3 recording stations only. There may be some minor errors here and there depending on the geology and other factors. But normally, it's not determined only from 3 recording stations. There are thousands of recording stations in the world. So when they calculate from all of them, the error is minimized. And the average finally shows very small error. So you can find it with 98, 99% accuracy where the earthquake occurred using several recording stations. Well, now the 3-circle method, it depends. There is some assumption which says we know exactly where the soil property, what the soil property is, the shear wave velocity and the P wave velocity. How about if you don't have the shear wave and the P wave velocity for a local area? Then you can use a general chart. There are general charts, travel time curve method, which is using the P wave. There are general like a P wave and S wave charts, and distance travel from earthquake center and time elapsed after start of earthquake. You can use these charts and use a recording station to estimate where it occurred. If you don't know the local soil properties. If you know the local soil properties or rock properties within a recording station, you can use the 3-circle method. But if you don't know it, and if you want to find it approximately, there are general charts prepared. Let's say you have 3 recording stations, seismogram A, seismogram B, and seismogram C. Seismogram A shows the time difference between the P wave and S wave is 3 minutes. So try to find on that S wave, P wave chart, try to find where the difference is 3 minutes. Seismograph B shows it's 8-minute interval. Try to find that. Now, with the 8-minute, as soon as you find that 8-minute interval, you are exactly finding also the location, the distance. The horizontal axis is telling you this is about 5,500 kilometers for 80-minute interval. For 3-minute interval, it's around, this is, let's say, 1,000. This is about 1,500 kilometers from recording station A. 5,500 kilometers from recording station B. And a recording station in location C, it shows the time interval is 11 minutes. These are just an example. So if it is 11 minutes, when you fit that, you'll find approximate distance, epicentral distance, which is this is 9,000, so maybe 8,600, 700 kilometers. So now you have your distances. You can use these distances and the 3-circle method to find the location of the earthquake. And section 1.7, intensity and magnitude of earthquake. once we record an earthquake, we want to quantify it. We want to, there are terms like intensity. What's the intensity of the earthquake? Or what's the magnitude of the earthquake? Usually in Richter scale. So when we talk about intensity, like let's say an earthquake occurred, then people go out and survey the area, survey the damage. What happened? How bad is the damage? So you have all these Mercalli intensity scales, up to, I think, 13 or 14 of them. 12 of them. So scale 1 is MMI, is modified Mercalli intensity. So you do your survey, you know how the damage is. In some cases, it may not be even felt by people. For example, intensity level 1 is, it's not felt except by very few under especially favorable circumstances. If that's the case, this is an earthquake with intensity 1. Let's say earthquake of intensity 5. That one is felt by nearly everyone. Many awaken from their sleep, and some dishes, windows, it's broken, a few instances of cracked plaster, unstable object overturned, and so much. So these are the terms that you can categorize. From your survey, you can fall into number 5. Or if it is a severe earthquake, you can go to the list to find what exact intensity level exactly matches the survey. If you see intensity 10, is some well-built wooden structures destroyed. Most masonry and frame structure with foundation destroyed. Ground badly cracked, rails bent, and so on. Or the last intensity, the 12, is a total damage, waves seen on the ground surface. This you see where you see those surface waves, relay waves and lava waves. Lines of sight and levels distorted, and objects thrown upward into the air. So this is just intent. So when we talk about the intensity, when you describe earthquake in terms of intensity, it's based on the level of damage, the degree of destruction. So this is based on survey. You have to do a survey, go to the area, assess the damage, and try to categorize what level it is. You don't hear probably more often about this way of quantifying earthquake, but it's common to see on the news about earthquake magnitude, like a Richter scale. That's the most common. We say, okay, a magnitude of 6, 7, or 8 happened. That's the earthquake magnitude, usually in Richter scale. Charles Richter developed the most widely used scale for shallow and local earthquakes, epicentral distance less than 600 kilometers in Southern California. This is the first one to develop like this, but I forgot what year it is, but in the early ages. So what Richter does is, once you have a record from an earthquake, and it's a logarithm of that amplitude, is what the Richter scale is describing, the local magnitude. Amplitude is, let me take you back to the record. The amplitude is the peak, the maximum you have. Let's say if the maximum is this is the amplitude, the peak. You can measure it in millimeter, and that's what you use in that Richter scale. When we say A, that's the amplitude. A denotes the amplitude in microns or in millimeter, recorded by the Wood-Anderson seismograph instrument located at epicenter distance of 100 kilometers. This is specifically prepared for a specific case, for epicentral distance of 100 kilometers. But we have earthquakes which are different from 100 kilometers. It can be 50 kilometers. It can be even more than that. So there is a calibrated, a modified form of Richter scale. So what you do is in Richter scale, you have the amplitude, do the logarithm. That's what this is telling you, the vertical axis, the log of the peak amplitude in millimeter. Let's say if you find something like 1.5, the local magnitude says 1.5. Now, depending on what distance you are, let's say you are around 200 or 250 kilometers away. So you can pick that and see where you are meeting. So this will give you an earthquake of magnitude of around 5. So that's what the Richter scale does. But Richter scale is not the most advanced way of determining the earthquake magnitude. There are so many advanced, like a moment magnitude or surface wave, body wave magnitudes recently developed. So I want you to go to this reference one, section 292, and look at those. There are more additions to, for error minimization and local effects or the fault characters. If a ground fault occurs, then they assume also the fault rupture dimensions. So there are more advanced equations developed after the simple Richter scale, but we still use the Richter scale nowadays. So you can go, this is a reading assignment, go to your reference and see this section to see the other equations. And just to give you an example on the Richter scale, let's say from seismic record, if amplitude A is 23 millimeter, let's say you have this seismic motion and the peak amplitude is 23 millimeter. This is a displacement record. And SP time, S is the difference between the shear wave and the P wave time, this duration. We initially record P wave at the beginning, then after a while, the S wave comes with a larger amplification, with a larger peaks. And that SP, let's say for this example, 24 seconds. So if you know the peak value, so the local magnitude from the Richter equation, it gives you 1.4, logarithm of 23 to the base 10. Then you can use that modified from Richter chart. There is also, if you have 24 seconds, the time duration between S wave and P wave, using that distance equation, what distance it is from. So you can use either the distance or you can use the time. This is also another way of presenting the Richter scale. And you have amplitude. Amplitude is at 23 millimeter. You can use the chart on the left or the chart on the right. They're pretty much the same. So 23 millimeter, amplitude is 23 millimeter. You can enter it this way. And also the distance, SP time duration is around 23, or in terms of distance, it's around 220 kilometers. You can use this. If you connect these 2 points, then you'll pass by this magnitude. This is just showing earthquakes only up to probably 6.5, but it can be extended to capture larger earthquakes. So same is true with the other chart. For the horizontal vertical axis, you get 1.4 for the local magnitude, and you know that your distance is for 24 seconds 220 kilometers. So you can use 220 kilometers, and finally you'll get around 5.1 on the Richter scale. So this is a simple way you can determine it, but this is a Richter scale, like I said, but I want you to go to section 292 on the Kramer book and read about a more advanced way of determining magnitude of an earthquake, like a moment magnitude, which account for the fault rupture dimension. And there are also surface wave magnitude and body wave magnitude. Because the Richter scale, it doesn't tell whether it's a surface wave amplitude you are using or the body wave using. It's just the peak value that's peaking. So this concludes the first chapter, just giving you a background on earthquake, what they are, how we record them, what damage they cause. And there is a reading assignment, chapter 1 and 2 of reference 1. So if you go to reference 1, that's the best reference I found for this chapter. Just read chapter 1 and 2. You'll find more details on what the class discussion is. And so the Kramer book, you all have it, or Bahardar University has it. So you can get a copy from there and read those chapters.